Why work with rectangles when you can work with circles? Yeah, that won't be complicated at all. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are delving into the world of nonlinear coordinate systems, an exciting and mysterious place. Most of us are familiar with rectangular coordinate systems. That's x and y in 2D and x, y, z in 3D, but we're gonna stick with 2D for now. But there are other types of coordinate systems out there that don't depend on squares and straight lines to describe them. Enter polar coordinates that use circles as their point of reference. Whereas in Cartesian or rectangular coordinates, I have x and y, in polar coordinates or circular coordinates, I have r and theta. Whereas x describes a horizontal position and y describes a vertical position, r describes a radial position and theta describes an angular position. For instance, let's plot the point 8, 8 on the xy plane. That means I've traveled 8 units in the horizontal direction and 8 units in the vertical direction away from the origin. In polar coordinates, I could write it like this: 8 square root of 2, pi over 4. That first number describes r, how far I am radially away from the origin, and that second number describes theta, which is the angle away from the positive x-axis. These two coordinate points, 8, 8 and 8 square root of 2, pi over 4, describe the same point in space, just using different coordinate systems. Notice that I'm using radians here for my angle measurement. We tend to understand what a degree measure looks like on a graph more so than what a radial measurement looks like on a graph. But radians are a whole lot more useful to use than degrees, not the least of which is because they are a unitless quantity. So I'm going to be using radians here and only talking about angles in degrees when we have a measurable angle, like an angle of declination or an angle of inclination. Now, looking at these two coordinate points, it may seem that we have complicated things more than we've helped, and in a way, that's true. There are certain things in polar coordinates that become a whole lot more complicated, but complicated things in Cartesian coordinates become much simpler in polar coordinates. So let's take this example. X squared plus y squared is equal to 4. If you've been introduced to conic sections, you might recognize that this is just a circle with a radius of 2. Now, in Cartesian coordinates, we get this kind of complicated relationship. But in polar coordinates, well, let's think about what this circle actually is. A circle is the set of points that are exactly r distance away from its center point. Since the center of the circle is just 0, 0, the polar relationship for this circle is simply r is equal to 2. That describes every point that is 2 units away radially from the origin. And that's it. That's the nice simplicity of using polar coordinates for this example. Beyond circles, things like spirals or cardioids are more elegantly described using polar coordinates than they are using Cartesian coordinates. Take this cardioid, for example. In polar coordinates, it looks like this, but in Cartesian coordinates, it looks like this, which is a lot more complicated and not as fun. But so many of us use Cartesian coordinates so often that working in polar coordinates can be a bit strange. Fortunately, there are several easy transformations between these two coordinate systems. So say I want to find my x coordinate based on an r and theta. So first, let's draw a circle of radius r centered at the origin here. Let's draw a line from the origin out to a point on the circle, say x, y. Let's drop a line from that point, x, y, down to the x-axis. That line is y units long. Now, from the intersection point of the x-axis and that line we just drew, let's draw another line back to the origin. We know that the length of that line is x units. So now we've made a right triangle with a hypotenuse of r and 2 legs of x and y. Using some right triangle trigonometry, I can find that x is equal to r cosine theta, where theta is this angle here that leads up from the x-axis, and y is equal to r sine theta. Now, what if I want to convert from x and y over to r and theta? Well, I have some relationships there too. I can see that r is just equal to the square root of x squared plus y squared. That's the Pythagorean theorem. And using some trigonometry again, I can see that the tangent of theta is equal to y over x. Now, something to keep in mind with polar coordinates is that the angle theta can take on any value from between negative infinity and positive infinity. But the added complexity of polar coordinates is that because the angle is circular in nature, it's going to pass through the same relative position multiple times. So for any given problem, I might have many solutions for theta. So for instance, this point here where theta is equal to pi over 4, is the same thing as 2 pi plus pi over 4. They describe the same angular position. Okay, so let's jump into an example. Let's take this point -7, -12 in the xy coordinate system. How can we convert that into r and theta in the polar coordinate system? Well, I know r is just the square root of -7 squared plus -12 squared, and doing a little bit of math, we find that that equals about 13.89. But what about theta? Okay, so let's take the tangent of theta. We know that that is equal to -12 over -7. Taking the arctangent of both sides, we find that theta is equal to 1.04 radians or thereabouts. But before we continue, let's graph theta. 1.04 radians is about here on the xy plane. But we know that our xy point is here in the third quadrant. So what's going on here? Well, when we take the arctangent of theta, we find that arctangent is defined between the values of -pi over 2 and pi over 2. So when we take the arctangent of any number, our calculator will only spit out answers that are between -pi over 2 and pi over 2. Now, the third quadrant stands outside of that range, but that doesn't mean that answers don't exist there. But as we can see, if we graph these 2 points, 13.89, 1.04 out here in the first quadrant in polar coordinates, and -7, -12 out here in the third quadrant in xy coordinates, we see that they are collinear with the origin, which means that they are 180 degrees away from each other. So if I add pi radians to my 1.04 radian answer, I get the true answer to this problem, which is about 4.18 radians, which brings us to the third quadrant here. So the full answer to what is -7, -12 in polar coordinates is 13.89, 4.18. Now, of course, as we brought up earlier, I can always add 2 pi to my theta answer and get the same radial position. But we often restrict our answers to theta to certain domains. So for instance, let's restrict it to 0 and 2 pi. And we find that this is the only answer that fits the bill here. Now let's talk about one more thing, which is, can r be negative? And some people would argue that yes, r can be negative. And what that means is that if I were to take the point 13.89, 1.04 and make r negative, that flips the position of that point across the origin and brings it down to the third quadrant here. So now we can see that the point -13.89, 1.04 is equivalent to positive 13.89, 4.18. However, to eliminate this ambiguity, we often restrict r to values between 0 and positive infinity. As always, if you have any questions, leave them in the comments below, along with any suggestions for topics you'd like to see covered in future episodes. Be sure to hit that like button, subscribe, and hit that notification bell so you never miss another math, physics, or problem-solving tutorial. I also offer one-on-one online tutoring sessions for students of all levels, so send me a message. Thanks so much for watching, and I'll see you in the next problem.